Hello and welcome to York Universe, the astronomy and astrophysics radio podcast written and presented by the students, faculty, alumni, and friends of York University. You'll find us now wherever podcasts are distributed. I'm Senna Withers. I'll be one of your hosts this evening, and I'm joined by Paul Mackin. We're broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night at 9 p.m. local Toronto time or Tuesday morning at 1 a.m. Universal time. We broadcast live on our YouTube page, York Observatory, and run in concert with our online public viewing program run by the Observatory team. To navigate to our live show or to find out more, please check out our website at yorku.ca/science/observatory and follow the links to the online public viewing to join the live chat on YouTube. For any questions or comments you have on any of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can also always connect with us on Instagram with the handle @YorkUObservatory and on Facebook at Allan I. Carswell Obs. All of our programs are free, but if you would like to make a donation, please see our website at yorku.ca/science/observatory. Our OPV crew will be monitoring the chat room for any questions and to post content. The current weather is actually quite nice here in Toronto at the observatory, so we'll be doing some live observing for you tonight. And our observing crew has a bunch of really great objects prepared to show you live through the 1 meter tonight if the weather holds up. So Paul, how are you?
I am well. You're speaking of beautiful nights. I call this the halcyon days of second summer. We're getting beautiful weather, and for all the bad run of weather we had in the summer, what we're getting now is phenomenal. I've just commissioned a new astrograph, and I've got it out there every night, just capturing more data than I can possibly deal with. But that is the way of things for astronomy.
Yeah, I mean, it's always good to have more data than you can handle than not enough. You know,
Absolutely,
as as
absolutely.
as tiring as observing all the time can get, it's definitely better than the alternative of just like, never going observing because the weather is too terrible.
Well, I'm going to make an editorial comment here. I had to be at the observatory till 2 o'clock in the morning a couple of weeks ago, and Suna, you were there. And for me, that's a relatively rare event. But for you, that's just about continuous. So you've got
Yeah,
incredible stamina, buddy.
it's a lot of fun. Observing is great, and I know there's a couple other of the observatory crew who likes to stay till that hour. We might be a little bit insane, but it's definitely worth it for
Well,
all the
last
good
night,
data.
I think it was last night, one of our other team, Hector, uh, was was there late, and he was going to be observing. And we every year, as and this is kind of a plug for Christmas, we publish a calendar, and we're putting the images together for that calendar now. This will be available online and through the bookstore. But we actually said to Hector, we have no pictures of planets, and there are really no planets in the sky right now except Saturn, and its rings are on nearly on edge. So can you stay a little later and get some shots of Jupiter? And Lord love him, I mean, he was there till 6 o'clock this
Oh
morning,
my God.
but he got it. So when it
Yeah.
comes time to buy a Christmas present or a stocking stuffer, think of Hector.
Yeah. Yeah, sometimes it's worth it to just stay the extra bit to get some pretty astrophotography. I know that we're now approaching the time that Orion is up very early in the morning. So that's the thing that I like observing. It's my favorite constellation. So I will stay up to ridiculous hours just to get a peek at Orion. Um, but
It's
pretty
funny
soon.
because I was observing. I had my new astrograph observing the Great Nebula in Orion last night, and tonight it's doing the Horsehead Nebula. So, yay Orion!
Yeah, yeah. I love that constellation. It's just packed with so much really, really cool stuff. So I can't wait until it's up in the evening. But we have a really interesting show prepared for tonight. Starting off with our space and astronomy history, I'm starting us off with not only an important history item for just space exploration and astronomy, but also an important item for Canadian history, which was September 29th, 1962, when Canada launched its very first satellite called Alouette 1. Now, not only was this the first time that Canada ever launched a satellite, but this was also the first time that, or sorry, this was also the third nation in history to launch something into space. This was, of course, following the USSR launching the Sputnik satellite and the United States launching the Explorer-1 satellite. But I think it's pretty cool to think about the fact that Canada is only like the third nation to actually launch something into space, especially coming after other much larger countries with bigger space programs. But anyways, Alouette 1 satellite was primarily run by Canada. This was before the time where the Canadian Space Agency was active. It was not formed until I believe it was the 1990s, and we're in 1962 here. So at the time, the place that was running the Alouette 1 mission was Canada's Defence Research Telecommunications Establishment, or the DRTE, and they were working in collaboration with the United States and the newly formed organization of NASA. Prior to NASA being formed in around the 1960s, the United States space program was actually run by the NACA, so swapped out the C for an A and kind of changed up the acronym, but we were working with basically the newly formed NASA. And essentially, the reason why Canada was collaborating with the United States is because the United States has a lot of essentially infrastructure and other things that you need to launch satellites that the Canadian government didn't have access to at the time. So this was things like testing and launch capabilities that the US already had in place. And the deal was that Canada would design, build, and pay for all of the entire satellite, and then it would hand it over to the US to do testing before a launch, and then to actually perform the launch itself. So the Alouette program essentially was designed to study the upper atmosphere of the Earth, particularly the ionosphere. Now, this is a part of the Earth's upper atmosphere starting at an altitude of around 50 kilometers or so, where harsh UV radiation coming from the sun is actually able to ionize most of the particles that are in the Earth's atmosphere. So you end up with this part of the atmosphere that's mostly ionized, called the ionosphere, while at lower altitudes, the rest of the atmosphere is primarily neutral. And it was around this time in 1962 that people were starting to realize that the ionosphere could actually have impacts on a lot of day-to-day activities that were starting to become more popular and more required, and a lot of things that we actually rely on very, very heavily today. So things like GPS signals and radio propagation in the upper atmosphere is all affected by the ionosphere and conditions in the ionosphere. So this can really impact a lot of long-range communications or radio signals. And it was kind of around this time that scientists and engineers are really starting to pick up on the fact that this is a very important part of our atmosphere. So Canada decided to launch a probe that was actually meant to study the ionosphere. So not only was Alouette 1 kind of an important probe to actually study the atmosphere and understand from a more scientific point of view what was going on with the ionosphere and the impact that it has on communication systems, but it was also required a lot of really interesting engineering, which essentially just comes from the fact that they had to fit this entire satellite into a 1 meter diameter little capsule to actually launch it. So the satellite itself couldn't be more than 1 meter in diameter upon launch. But in order to detect the kind of radio waves that Alouette 1 needed to detect to study the ionosphere, it needed an antenna that was about 45 meters in diameter. So engineers ended up coming up with something called the STEM, which is the Storable Tubular Extendable Member for the spacecraft, which would essentially just roll up this massive 45-meter long antenna. And then after it was launched, when it was in the right position, it would just use a motor to unwind this massive antenna and allow it to do the research that it needed to. And particularly what Alouette was looking to do is it had 4 different instruments on board, including that massive 45-meter diameter antenna. And it was really just picking up on various types of radio waves and radio noise in the upper atmosphere, and also studying the types of charged particles that were in that atmosphere. So Alouette 1 launched on September 29th, 1962, aboard a Thor Agena rocket from California. And in total, it lasted 10 years in space, even though it was only designed to last for 1 year. So, right off the bat, Canada was, I guess, part of that under promising and over delivering thing that NASA and I know a lot of space agencies always do. They always under promise and then over deliver with missions extending for much, much longer than they had originally been planned. So not only was this a very important satellite from a scientific perspective, it also led to three additional satellites, actually, which included a collaboration between the United States and Canada. This includes the Alouette 2 satellite, which was essentially just a modified version of Alouette 1, and then two other different types of satellites called the International Satellites for Ionospheric Studies number 1 and 2. So Alouette 1 really helped to kind of just establish Canada's place in space exploration, not only from an engineering perspective that Canadian scientists and engineers could design these great satellites, but it also helped us establish from a scientific perspective that Canadian scientists are really good at studying the ionosphere and can do a lot of great work in that area. So happy anniversary to Alouette 1.
Yeah, at the Ontario Science Centre, which is now lamentably closed, I guess, they used to have a model of the Alouette. And I hadn't been there in a few years before it closed, but I imagine it was still there. And it kind of does look like you'd expect a satellite from the 1960s, but it was huge when you extended the booms out all the way. Interestingly, one of the other side effects of the study was, as the 1960s evolved, they needed really good ways to communicate around the world. Didn't have oceanic fiber optic cables at that point. Satellites hadn't been deployed yet for communications. So one of the things Alouette did was help give data to develop some models, not for the ionosphere, but for lower down the troposphere, tropospherical scatter, because it's basically the same electrical activity, the same kind of electrical influence as in the ionosphere. And I knew a number of engineers older than me who worked on tropospherical scatter. So what they would do is have these monstrously large dishes, and they basically blast up signals into the upper atmosphere, and a certain percentage of them would bounce back down and somewhere else. And you basically, depending on the angle of the dish, you could set the point of coming down. But the Alouette helped provide data for modeling that. Canada was actually a leader in communications. We also did our own cross Canada phone service, and we did the DO line. And this is where one of the places we really excelled at that time. Now we work in more conventional space science, but this was kind of the engineering and telecommunications aspect of it.
Yeah, so it was I kind of love a lot of these projects because while it was meant to study the ionosphere, like you said, it did have other kind of implications for studying the troposphere as well. It's really awesome how one of these satellites, you can kind of design it to do one thing and then it could just actually do so many other things at the same time.
Yeah, but more modern, a little more modern, but still in space history. On September 26th, 2022, the DART spacecraft, which stands for the Double Asteroid Redirection Test, was intentionally crashed into the asteroid Dimorphos, which is satellite to a larger but still really tiny asteroid called Didymos. Now, asteroids often come in pairs. It's not, we've seen a fair number of pairs out there, and we've seen, some objects which are binary, which means they're two asteroids, but they're actually physically joined, and they have a moon around them, and so on. So you get some very complex geometries with asteroids, but this was for humanity's first attempt at planetary defense, and it was a success. So the idea was very simple. Find an asteroid pair. So that's two asteroids orbiting, well, the smaller one orbiting the bigger one. They're actually both orbiting each other around a common center of gravity. But we had to have, well and accurately documented orbital characteristics. We had to know down to pretty much the millisecond how long it took for this little orbital dance to play out between them. And then what you do is you smash a spacecraft as massive as possible and at high speed as possible into the smaller of the two asteroids. This would affect the orbit of the smaller asteroid And then we begin to understand the how effective the idea of an impactor could be in changing the orbit of an asteroid or comet that might hit Earth. Now, Didymus was small, which is only about 850 meters. It's kind of elongated, but roughly kind of like a football, 850 meters, and at the short axis, about 600 meters. Dimorphos is much smaller, 180 by 120 meters. These are not big things, and they're a long way away, and they're moving. Uh, but they've been observed for a long time, and their orbit around the sun was well known, and their orbit around each other was well known. So the DART mission was launched in 2021, and about 10 months later, it steered itself. And that's an important point. It wasn't guided in. It basically had software, and the software was tested on the way repeatedly, that could see Didymos and then identify Dimorphos and fire its thrusters to aim for Dimorphos. So it steered itself in completely autonomously with no impact from mission control, and it was taking pictures all the way in. And you can go online and see the pictures. It's you're literally watching a crash. It's getting bigger and bigger and bigger, and you can see rocks on the surface and boulders and things like that. And then suddenly the last frame just gets cut off partway through. But just before it hit, it also deployed a CubeSat, a small satellite, which was set to fly by the system. It wasn't going to crash. It was going to fly by the system, some distance behind and some distance away, and could take pictures as DART hit, and get pictures of the resulting dust plume afterwards. Now, on the website for this podcast, I posted a picture, and you can see what that CubeSat Lycrosat caught was called, what it was called, and it took these amazing pictures of this dust plume. So you can see that on the image website for this week's show. Now, subsequent observations confirmed that Dimorphos's orbit changed from 11 hours and 55 minutes to go around Didymos to 11 hours and 23 minutes. And this orbit was well known. This is not random. It's not a random variation. This is absolutely measured both before and after. So it's a 32-minute or just under 4.5% change. Really quite significant. This is a big deal because even the smallest change in an orbit made early enough will convert an extinction level event to a near asteroid flyby. And I always like to remind people the dinosaurs didn't have a space program. This is how we survive basically the insanity of our solar system firing rocks everywhere. So as a follow-up to this, the European Space Agency launched the Hera mission last year, which is going to rendezvous and go into orbit around the two moons. It's actually going to go into orbit around Didymos, like Dimorphos is, and it'll do that in December of next year. Its job is to do a complete survey, to look at the impact crater, to figure out how much dust is still there, how much is settled, if any other objects are now in a separate orbit, so we can start to get an idea of the dynamics of how all of this worked, and what that would mean if we were trying to model the impact of the deflection impact on an asteroid that was going to hit the Earth. So really a fascinating mission.
Yeah, I remember when this happened, and it was a really, really amazing thing to see that, you could actually defend yourself if there was, if you see it in enough time, you see an asteroid coming, you could actually defend yourself. It's also really interesting to think about this in kind of the context of a lot of the other major telescopes that have started to come online recently, like the Vera Rubin telescope in, I believe it's Chile. When you're taking these telescopes and you're doing such intense sky surveys over such short periods of time, you could actually theoretically detect a potentially lethal asteroid in enough time to launch a satellite to redirect it. And yeah, kind of like you mentioned, even though the 4% change is pretty small in in its orbit, that's definitely could be the difference between life or death. So it's a really fascinating, amazing thing that we can actually do that.
Yeah, and they actually have a number of different ways to do this. One is the impactor model. Another way is to have an even bigger spacecraft, the biggest we can build, and sort of put it in an orbit with the asteroid. And the gravity of that spacecraft, as small as it is compared to the asteroid, will subtly change the orbit of the asteroid. You don't need much, just a few, probably just a few centimeters per second squared is enough acceleration to make it miss the Earth if you've got a while. The other idea is also just paint it black or paint it white. Um, because in either case you change the thermal characteristics and the reflective characteristics of the asteroid, which means the amount of solar energy hitting it could also impact its orbit. So there's, planetary defense, we're going to end up with a number of tools in our toolkit. And if and when, and it's probably when we have to deal with this, we'll have options.
Yeah. I'm really wondering if at this point, like maybe I'm not sure which organization launched the DART mission, but like I'm kind of curious if the United States might have their own little, satellite that's there and ready to go if somebody does detect something with enough of a advanced warning. But yeah, because it would take quite a bit of effort to actually build a satellite and then launch it. So you would need a decent amount of advance notice, but
You
hopefully,
might. Yeah, it was a NASA mission, by the way. I think it was run out of JPL, I think,
okay.
but it was definitely a NASA mission.
Yeah. Um, yeah, it's great news that we can actually, defend the Earth from potentially lethal asteroids. But if we go back a little bit further in time, back to 1923, not really defending the Earth, not really defending the galaxy, but this was when our understanding of the universe and our place in it completely changed, which was on October 5th, 1923, when astronomer Edwin Hubble discovered a variable star in the Andromeda galaxy. So if we go back to kind of the early 1900s, and keep in mind that this is only like 100 years ago at this point, astronomers kind of believed that the Milky Way was all there was to the universe. They called the Milky Way an island universe, so there were tons of stars, nebulae, and gas and everything in our galaxy, and then nothing really outside of it. There were a couple of sort of reasons why astronomers at the time thought this, which included the fact that they knew the Milky Way was around 300,000 light years in diameter, and they were just kind of thinking that these distance scales are so massive that there's kind of no way that we can really get anything that's more massive than that. There were also a couple of other more scientific reasons why they believed this. But the problem was that at the time, a lot of astronomers were observing galaxies like the Andromeda galaxy that's visible to the naked eye under dark enough skies and the right conditions without the moon out. They were observing these other galaxies and basically just believed that they were part of the Milky Way. They were actually these really small structures that were kind of towards the edges of the Milky Way galaxy. But since they had this weird spiral shape to them, astronomers kind of nicknamed them spiral nebulae. Now, there was quite a bit of effort that went into studying these spiral nebulae to try to figure out their nature. So were they actually part of our galaxy or were they outside of our galaxy and actually millions of light years away and their own galaxies, their own island universes themselves? There was even what they call the Great Debate in 1920 between two astronomers, Harlow Shapley and Herbert Curtis, who were actually trying to argue their own points of view about whether or not the Milky Way was an island universe and whether or not there were actually other galaxies in the universe. So this was definitely a kind of hot topic in astronomy, and there was quite a bit of debate and back and forth about what these spiral nebulae actually were. Were they galaxies or were they just part of the Milky Way? But this issue was settled completely around 1923 to 1924 when astronomer Edwin Hubble was taking observations of what was then known as the Andromeda Nebula. And yes, this is the same person that the Hubble Space Telescope was named after, since he made a lot of really important contributions to astronomy at the time in a couple of different ways. And what Edwin Hubble was doing was he was essentially looking for a bunch of different stars in the Andromeda Nebula using photographic plates at the time because they didn't have CCDs or other typical astronomy cameras that everybody uses today back in 1923. So he was essentially just mapping different parts of the Andromeda Nebula and looking for various stars that changed their brightness over time. One of the reasons that looking for these stars was really exciting thing and a really important thing to do is because measuring distances in astronomy can actually be very hard. And it's really hard to distinguish between a very bright star that's very far away from you and a very dim star that's very close to you. So the planets, for example, the planets in our solar system, they look actually very bright to us in the night sky in a lot of cases. But if you were to start to go further and further away from our solar system, they would just start to look very faint, just because they are, pretty faint. We really see them only be from reflected sunlight. So it can be hard to determine just based off of the brightness of one star by itself how far away it is. So astronomers started searching for these things called Cepheid variable stars. These Cepheid variable stars are dying stars which vary their brightness in a really predictable way. So they basically go through this cycle of becoming very bright, then very dim, and then very bright again over a period of about 1 to 100 days in this case. Now, in 1908, the astronomer Henrietta Leavitt was studying these Cepheid variable stars in the small and large Magellanic clouds of the Milky Way. And she was able to establish something that's known as the period luminosity relationship, which is that the speed at which these variable stars cycle through their brightnesses is actually related to how intrinsically bright they are. And when you know how intrinsically bright something is, it becomes very easy to measure the distance, because all you need to do is compare how bright it appears to you to how bright it is intrinsically, and you can back out how far away it is. So Cepheid variable stars like these are just known as standard candles. Since we automatically know how bright they actually are, we can always use them to figure out how far away they are from us. So they're a very reliable distance indicator. And this was exactly the kind of thing that Hubble was looking for in the Andromeda Nebula at the time. He ended up picking out on a less than ideal night using the 100-inch telescope at the Mount Wilson Observatory in California, what is now known as the Hubble variable number 1, which is a little star on the outer reaches of the Andromeda galaxy. Now, this was following quite a long observing campaign with the 100-inch telescope at Mount Wilson, just because the Andromeda galaxy is really, really massive. Even through the 1-meter telescope, you have to image multiple different regions of this galaxy to actually take a picture of the full thing. So it was a pretty complicated thing to be doing, and he was also working with photographic plates. So this took a lot of work and a lot of time to actually be able to do. Now, the star that he identified on October 5th, 1923, the Hubble variable number 1, also labeled V1 for short, he had initially identified as a nova, which is a type of exploding star. But when he continued observing this nova V1 over the next few days, he started to notice that it was not changing brightness in the way that novas typically would. So he ended up taking further observations of V1 over the next 32 days, eventually getting enough data points to generate a light curve that shows how the brightness of the star changes over time, which is when he discovered it was actually a Cepheid variable star, not a nova. And since it was a Cepheid variable star, he could use the period luminosity relation of Henrietta Leavitt to actually figure out how far away the Andromeda Nebula really was. And the measurement that he got when he did that is it placed it around 1 million light years away from the Earth, which is absolutely, without a doubt, not in the Milky Way galaxy. So has to be, or some astronomers have called V1 the most important star in the history of cosmology, because it essentially started a lot of different areas in cosmology. There were so many amazing discoveries about our universe that followed from this. Not just knowing that there is more galaxies to the universe than just the Milky Way. So basically anything relating to distant galaxies, the expansion of the universe, the history of our universe, really all followed from Hubble's discovery that the Andromeda galaxy is more than 1 million light years away from the Earth. Now, over the next year or so, Hubble continued observing various stars in the Andromeda galaxy. He eventually ended up with a list of 36 variable stars, 12 of which were Cepheid variable stars, which proved very conclusively that M31 was not a galaxy, M31 was a galaxy. It was not a nebula like everybody had thought. So I think this is a really cool history item because it had a whole lot of very long-reaching consequences for astronomy and a lot of facts about the universe that astronomers today kind of just take for granted really came out of this discovery by Edwin Hubble.
Yeah, it's interesting. One of the first things you learn as an astronomy student is about the Hubble constant and how to do calculations based upon it. So this is absolutely fundamental to our understanding of cosmology. Interestingly, though, it's also Nobel Prize worthy, Nobel Prize physics worthy. He never got the Nobel Prize. And we'll hear in a minute, there are kind of two ways to deserve the Nobel Prize and not get it. And I guess Hubble was probably guilty of both of them. One is he apparently wasn't a very nice guy, brilliant,
Oh,
absolutely brilliant, but he had a huge ego and was difficult to work with. Uh, so one of the ways to not win the Nobel Prize is to be difficult. But the second way is that after he died, his family he really wanted it. So his family wanted the award to be given posthumously, and that's the second way. It can't be done posthumously. So he didn't get the Nobel Prize for it. He absolutely deserved it. It is to cosmology. This is the starting point of our modern view of cosmology, and a brilliant, brilliant man. But speaking of brilliant, brilliant people, I'm going to pick a little different item for history this week because none of this happened in October. But in 1966, a book entitled October the 1st is Too Late was published. That's my tie into October. Um, it's an unusual science fiction story in a couple of ways. It tells the tale of two friends. One's a physicist and the other one's a musician, both graduates from Cambridge University, and they suddenly find themselves in a world which has been separated into different time periods. England is their time, and it didn't change. Greece is at the height of the Greek Empire. They can't figure out what's going on in North America at all, and that's actually a key part of the story. And then Russia appears to be this one big, solid piece of glass covering basically the entire north of Europe, indicating that it's from the very far future when Earth is melted by an expanding sun. It's a really great little book. It's short, very readable. It's a fascinating story. It poses some really interesting questions about time and human perception of time. Uh, but it was written by someone named Sir Fred Hoyle. He was famous and infamous within astronomy circles. He's the person that first postulated nucleosynthesis. And that's a fundamental concept in basically stellar and planetary theory. But nucleosynthesis is the idea that the universe has coming out of the Big Bang, and we'll talk more about the Big Bang in a second. There was a lot of hydrogen, a little bit of helium, not much anything else. So stars formed, and as stars formed, they start to cook, in a way, heavier elements in their cores. And as the star explodes, it spreads them everywhere, and the explosion itself can create even heavier elements. So this is actually a very cool idea because there's a lot of hydrogen in you, in your water. There's also a lot of oxygen in the water too. There's carbon in you. All of those heavier elements came from the core of stars. So as people, every human, in fact, all life on this planet, we are made of star stuff. We literally come from the center of stars, which is fascinating. Okay. But he was also an advocate for the idea of panspermia, in which Earth would have been seeded by life in some manner rather than it's being spontaneously generated. There were some experiments around the same time by the work of Urey and Miller comes to mind, where they basically simulated the conditions on what would be a primordial Earth with an atmosphere. And uh, lo and behold, if they got the simulation right, amino acids occurred. and they could probably get them up to not proteins, but something getting closer to proteins. Um, so these are kind of two competing ideas. Something about ancient Earth, allowed for the complex organic chemicals that caused life to happen. The other idea is it came from elsewhere. Um, and there was no evidence to support the other idea. And the evidence for the first idea was, not, it was strong, it was compelling, but it wasn't complete. So now we can look at basically comets and asteroids, and we can examine material from outer space and from asteroid sample returns and whatnot. And lo and behold, there is a ton of complex organic prebiotic material in space, amino acids, complex compounds. So the idea, that panspermia, that life was seeded on Earth, probably not, but the idea that the chemicals which led to life could have come, as did a lot of our water, from comets and asteroids. So this idea of panspermia has some credibility. He also had a big controversy with the Big Bang, and I alluded to this earlier. He actually coined the phrase the Big Bang. He was the first person to come up with it, but he actually intended it as one of derision. He didn't like the idea of the Big Bang. He thought it was ridiculous, and you can get into the reasons. He did have actually philosophical reasons for this. He felt that if there was a big, he was an atheist, and he felt if there was a Big Bang, then you would need something to trigger the Big Bang. And that would lead to religious thoughts on this. That seems to have been one of his objections. And of course, there could have been another universe before the Big Bang. We don't really understand, the universe, the initiation of our current universe right now. Um, but he was an advocate of a steady state universe, which universe was always the same, always will be the same. And then he started, when we got information about the expanding universe coming out of Hubble's work, he modified the steady state theory, but never really let go of it. But these controversies were common with Dr. Hoyle. As he was once described as a scientist whose rudeness cost him the Nobel Prize. Or as I like to say, probably like Hubble, he was absolutely no fun at parties. But in addition to the incredible volume of scientific work, now I'm not much fun at parties either. But in addition to the incredible volume of his scientific work, he was also a credible author of fiction. And October the 1st is Too Late is a great read, along with a lot of his other books. The Black Cloud, A is for Andromeda. There's several others. Really, if you can find, they may probably be out of print, but they may be so far out of print that you can get them online for free. And October the 1st is Too Late is the best of them. So I certainly would recommend that.
Yeah, I guess that's kind of I was wondering what our theme for tonight's show would be, because a lot of the time we get like a little theme going. And I guess that's it, is astronomers who cost themselves the Nobel Prize for being no fun at parties. Um,
Well, it's
but
funny because I was thinking of it too, and I've come up with an idea for one, which was to boldly go, and we'll talk about that later. But Dart boldly went. So
yeah,
there's a couple of different ideas there.
yeah. But for anyone who's just tuning in, you're listening to York Universe, broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. Please visit our website, yorku.ca/science/observatory, to join the chat, ask any questions, and to see some live content being posted. Our observers are actually doing some live observing with the 1-meter telescope right now. They were just observing Saturn a few minutes ago. It looks like they're on an open star cluster at the moment. So lots of really interesting stuff over from the 1-meter. Tonight you've been listening to myself, Senna Withers, and Paul Mackin, as we were discussing some interesting astronomy history, including astronomers who cost themselves the Nobel Prize, and some general, fundamental physics and astronomy history. But before we get going to a couple of news items, we do have a couple of reminders coming up. First of all, there is a tour on Wednesday, October 1st, that's going to be hosted at the Arboretum parking garage on the 5th floor with our 40-centimeter telescope and some of our other smaller 20-centimeter telescopes as well. That's starting at 7 p.m. this week. And as usual, tickets are free, but we do ask that you book tickets ahead of time just so that we know how many people are coming and we can kind of make sure we're not having tons of people out at the Arboretum all at the same time. Also, if anybody's looking to do any observing this week, there's a couple of interesting things to look at. Particularly is that on Thursday, October 7th, early in the morning, the dwarf planet Ceres is going to be at opposition or very close to it around that time. So if you're looking to observe Ceres, this is a great time to do it. Objects at opposition tend to appear much brighter and larger in the sky than when they are not at opposition. So at the moment, Ceres is so bright that you can actually see it with binoculars or a small telescope if you're under good sky conditions. So if you're looking to do a bit of observing and want kind of a challenge, Ceres is a great thing to look at. And also, for anybody who loves the moon like I do, we are approaching full moon. It's a waxing gibbous right now. The moon is looking really nice out in the evening sky at the moment. So keep an eye out for some fun lunar observing if you like the moon. Paul, do you have any other reminders for anybody? Paul? All right. I'm going to take that as no reminders.
Sorry, I had the mute button on. I apologize. No, just get out there and enjoy the stars. I was going to say that a bit later in the thing, but this is a great time because the stars are starting to get, the skies are getting dark early. And the other thing I would say is that, with the nice weather, it's not particularly cold. Being an astronomer, an amateur astronomer in December is not as much fun as being one on a clear night in October.
Yeah, that's very true. This is like the perfect time of year for that too, because you can just take a couple blankets and some like tea or coffee or something and have like a cozy evening under the stars. So kind of perfect time of year to be going observing. But we have a couple of really interesting news items coming up. And I'm starting us off tonight with something that we've kind of discussed on the show a little bit here and there. I think we were talking about this last week as well, which is the idea of detecting exomoons. So these are moons that are orbiting exoplanets or planets that orbit stars that are not the sun. So there have not been any exomoons detected. And unfortunately, I'm not talking about a news item that found an exomoon. But this is actually a really interesting thing to study, not only because studying exomoons and their formation processes can help us understand a lot about our solar system. But if you think about the types of moons in the outer solar system, like in orbit around Jupiter and Saturn, these are very complex, dynamic worlds that could potentially, in some cases, host life. So instead of just looking at exoplanets and planets outside our solar system for potential signatures of life, a really interesting thing to do would actually be able to study the moons of these exoplanets and learn about the way that they formed, the conditions on these exomoons, and if they potentially have life or not. Now, the James Webb Space Telescope is probably the thing you're going to have to use to actually be able to detect these exomoons, at least at the moment it is. That might change with a couple of telescopes coming online in the next few years, but right now the JWST is kind of your best bet at actually being able to observe exomoons. And there was a team of astronomers who was not studying the exomoons themselves, but for the first time have actually been able to study the formation of a potential exomoon. So what they did is they were taking these observations with JWST of an exoplanet called CTCHA-b. The CTCHA is the name of the star, and then the B just stands for the exoplanet, which is around 625 light years away from the Earth. And as they were studying this star, it's a relatively young system that's only about 2 million years old. For reference, our solar system is 4.6 billion years old, so it's very mature and evolved in comparison to this very young 2 million year old system, which means that the star itself actually has this massive circumstellar accretion disk that's still around it. And from the accretion disk, you have a whole bunch of rocks and other nonsense coming from the formation of the star that's now condensing and forming into planets themselves. And then within these little planets that are forming out of these accretion disks, some of them can actually have their own accretion disks around that exoplanet. that could potentially go on to form their own moons. So what scientists studying this system and this exoplanet did is they were looking at the composition of the accretion disk around the star, which is the circumstellar accretion disk. They measured its compositions. They found evidence of things like water in that circumstellar accretion disk. And then they found this kind of little area in that accretion disk, but surrounding that exoplanet that they were studying, there was actually very carbon rich. And that kind of prompted them to take a little bit of a closer look at the system and figure out why there was so much carbon just concentrated in this little area around the exoplanet. Now, I want to point out that this is an incredibly complicated thing to do because stars are much, much, much brighter than their exoplanets and the exomoons potentially that could be surrounding them. So scientists had to kind of employ a lot of very complicated processing techniques and get very creative to actually be able to sort of detangle the light that's coming from the star and the light that's coming from the exoplanet and its disk of debris that surrounds the exoplanet. But ultimately, what they were able to do is actually find evidence that there is a disk surrounding that exoplanet that could go on to form moons. So it's basically found the precursor to an exomoon around an exoplanet, which is not something that has ever been done before. And very importantly, one of the things that they discovered around this exoplanet is that that disk is very, very rich in carbon and molecules that have a lot of carbon in them. So this is including things like acetylene and benzene. There's a whole lot of that around this little accretion disk around the exoplanet. And ultimately, what this indicates about that system and that exoplanet is that there was a very rapid chemical evolution that happened over the course of 2 million years. And they just know this because of the very large difference in the type of molecules and chemicals that are in the accretion disk surrounding the planet and the larger accretion disk that surrounds the star. So observations like these are very important just from sort of a perspective of, wow, this is really, really cool that we're actually able to do this now. But they're also very important from the perspective of the fact that we can now study directly the formation of moons surrounding planets. This is very important for doing things even like understanding our own solar system and the history of our solar system, because it's currently believed that the very large moons that surround planets like Jupiter and Saturn were formed through a very similar process. So by studying the physical processes and the timescales associated with the formation of these disks and eventual exomoons around exoplanets, it also tells us a little something about our solar system. So I was actually planning to do a different news item tonight, but I saw this posted online today, and I just think this is really, really cool. Hopefully we'll be discussing an exomoon discovery pretty soon too.
Yeah, it's kind of interesting. Exoplanets, the first credible exoplanets were detected in 1998. And I mentioned that I'd been in the observatory with you, Suna, until 2 o'clock 2 Fridays ago. And that was to look for an exoplanet. I wasn't trying to discover one, but my observing team was tasked with trying to identify one that was already there. So to give you an idea, to give our listeners an idea of how hard this is, using the transit method, you're looking for a 1 part in 10,000 drop in the light levels in the particular exoplanet we were looking for. But as we use this technique and other techniques, the number of exoplanets has now exceeded 6,000. And if you think about it, that makes sense. I mean, why should the solar system be special? Every single time we think we're special, we find out we're not. Okay. The Earth was the center of the solar system, right? You know, it wasn't, right? The sun was near the center of the universe. That was actually a pre-Hubble belief. It was near the center of the observable universe. It wasn't, right? So why should we be the only solar system with 9 planets, or with a number 8 planets, with a number of planets? But then you start to ask the question, well, some of our planets have moons. Some of them have a lot of moons. Saturn's up over 200, I think. And why should planets in other solar systems not have moons? It makes sense they would. Of course, this you could follow this logic down to an eventual conclusion that what about life? Is life unique to Earth? Probably not, right? Is intelligent life unique to Earth? Probably not. We discover things as we go on, and this is I think 10 years from now we'll be talking about exoplanets and exomoons, and we'll be talking about their atmospheres in detail, the planets, and maybe the moons in some cases. So this is all part of the evolution of that we see in our understanding of the universe around us. I've said it before. If you're going to be interested in astronomy, this is a great time to be alive.
Mm-hmm. Yeah, I am really, really hoping on the discovery of exomoons because I don't know, there's not really a doubt in my mind that they exist because kind of like you said, we're not special. So if so many planets in our solar system have moons, I really don't see why other planets in other solar systems wouldn't have moons. But yeah, it is kind of just a matter of time before exomoons are discovered, I think. And I'm really hoping to see news articles about this because there have been actual dedicated searches to not only exomoons, but now actually there's more searches about the debris disks that are forming those moons thanks to this new discovery that was recently published. So there will definitely be a lot more interesting things coming out of this. But we are getting close to the end of the show, so I'm going to pass over to you for our final item this week.
Absolutely. So I was actually anticipating some bad news for this week's podcast, but fortunately not. Last week there was a news item, breaking news actually, which I guess tells you what a big deal this individual is, that Canadian actor, thespian William Shatner was rushed to hospital for a medical emergency. Now, when the words medical emergency are used in conjunction with age 94, the outcome is often grim. That being said, Mr. Shatner got through it and is still with us. And after correcting some problems with his blood sugar, appears to be healthy for a man his age. Of course, William Shatner is an actor, and this is an astronomy and space podcast, but Shatner has had a significant impact on generations, and I mean, yes, generations of astronomy and space enthusiasts. Playing Captain, then Admiral, then Captain again, James T. Kirk of the Starship Enterprise on 76 episodes of Star Trek, the original series, and then 22 episodes of Star Trek, the animated series, 6 motion pictures as lead, and 1 Generations as significant supporting character. That in itself is just a huge volume of work. And I watched Star Trek on its original run. I'm in my mid to late 60s now, and the very first episode I watched was called The Alternative Factor, and I was hooked from the get-go. A relative suggested that I watch it, and I basically said, "Oh, maybe," and I turned it on, and I haven't stopped watching it since. And like so many people of my generation, that show, coupled with the coverage of the space race, which was going on at the same time, nurtured a lifelong love of astronomy and space travel. However, what Star Trek got right was both technologically and socially important. It was woke before the term existed. It addressed social injustice issues from the very beginning. It had a mixed race and mixed species crew with major Black and Asian characters. It addressed the themes of prejudice, racism, and equal rights long before they were commonly explored in popular entertainment. And on the technology front, wow, you could argue that Star Trek predicted mobile communications, advanced technology, medical sensing, computers as part of daily life, as well as rapid and easy access to space. the list goes on. We won't get into it all here, but it is really impressive. And as an editorial, there is a show. It's available on pick your favorite streaming service called How William Shatner Changed the World. It's a bit of a comedic show, but it talks about all the technology things that Star Trek has introduced, not just the original series, but all of them. But Star Trek went on to work, sorry, Shatner went on to work on other things as well. He's had a long and successful career uh, in shows such as TJ Hooker and Boston Legal, which is a favorite of mine. He also appeared recently in his 90s as James Kirk again in sort of a tribute film for Star Trek by a group called OTOY, which is associated with the Gene Roddenberry Archive. Gene Roddenberry was the creator of Star Trek. The film's name is 765874-Unification, and it's available online for free. It is a lovely bit of work. Actually, it's just a sweet tribute to Star Trek. It's very ethereal. It doesn't really have a linear story, but it's just sweet. He remains one of the three remaining original series actors, along with the other two are George Takei and Walter Koenig. And while they're all getting up there, Shatner is the oldest. But what is really cool is that Shatner is actually an astronaut. He flew into space on New Shepard's 18 suborbital flight in 2021, and he flew high enough to qualify as an astronaut. He's apparently overwhelmed by the experience, and he's commented on the visible fragility of our planet, and how we have such this great place to live that's tuned for us to live in, and we could destroy it. And so he wept what he saw, and I thought that, and it was quite heartfelt what he talked about after that flight. So I will say, before we go to, I guess, our sort of closing comments and thoughts, from one Canadian to another, Mr. Shatner, you have already lived long and prospered. Keep doing it.
Yeah, it's really amazing to think about like the kind of impact that people who aren't astronomers can have on just the field of astronomy and the public interest in astronomy. Because like you said, there's so many people who took on this really great interest in this field because of shows like Star Trek and because of people like William Shatner. So it's a really amazing thing to just think about. And the interplay also between sci-fi and astronomy and space exploration in general is also like very real. There's a lot of things that astronomers discover that just look like it's like straight out of some sci-fi movie or novel. One of the interesting things I also always remember is when the United States was starting the space shuttle program, people kind of put together this massive like campaign to get the first space shuttle named Space Shuttle Enterprise after Star Trek, after the Enterprise on Star Trek. So there's definitely a lot of like, yeah.
There's this great little picture of the entire main bridge crew of the Enterprise attending the christening of the Space Shuttle Enterprise. And the only one that wasn't there was Shatner.
Oh no!
He had a prior commitment. It was done very much last minute. Ironically, of course, the Enterprise itself was the only non-flight ready space shuttle. It could fly in atmosphere, but it was never planned to actually fly in space. I've seen it, and you can actually tell the outside is plastic, not the tiles and things like that. So it's yeah.
Yeah, that was the first space shuttle I saw was Space Shuttle Enterprise. But nonetheless, it was still a very important space shuttle for the program because they did a whole bunch of testing and everything on Space Shuttle Enterprise. So it's always really fun to see that kind of the kind of interaction you get between sci-fi and astronomy and space exploration because there are a lot of ways that they are related to each other. And you always want to get more people. You always want more people, learning about astronomy and getting interested in astronomy, and sci-fi like this is an amazing way to do it. So
and if you think about it, Star Trek now 2025, 60 years later, is still going. It's basically its own streaming service.
Yeah. Yeah, that happens. I've seen that happen, I think, a couple of times with sci-fi, like even with Doctor Who, it got rebooted and it's still running even years later. So it's really great how you can get these really crazy long running series and everything. It really shows there's just a lot of public interest
It
in this sort
does.
of thing. Yeah. But yeah, definitely glad that William Shatner is okay. So I guess we're ending tonight's show on a happy note, thankfully. So for everyone who has been listening, you've been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Paul Mackin and myself, Sana Withers. You can always connect with us on Instagram at the handle at York U Observatory and on Facebook at Allan I Carswell Obs. You can also check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in to York Universe, clear skies, and have a good night.
Have a good night, everyone.